Okay, you ready for another one? This one actually is an easy one. So here, let's make sure we understand what the problem is. All right? There's some M star that is special, and we're going to later get to decide what it is. All right? We can have M prime be any special thing we want. It's some fixed Turing machine. All right? And what's the problem? Is the input is going to be some I, and we want to know, does our special Turing machine halt on I or not? Right? So if you can imagine if M prime was an easy problem, is an easy Turing machine, you give me an I, I'll know what this Turing machine does. Right? But we're going to make M star a hard problem so that this will be undecidable. All right? So how do we do it? We assume that we have an oracle that solves this problem. And then we're going to come up with, we're going to design an oracle that solves the halting problem. Right? And so we're given an M and an I. Right? We want to know, does M and I halt? Well, what do we give? We got to do an instance map. Right? We got to map this M and an I to some input that we give this guy. Right? And what do we have to tell? What do we have to tell this oracle? Just information theoretically. Do we got to tell him our M? How is he going to know whether our M halts if we don't tell him our M? Do we have to tell him our I? We got to tell him our M and our I, right? But we got to package it in a way that he can accept it. What does he accept? What does he take in? He takes in inputs. What's an input? It's a 0-1 string. What do we got to give him? We got to give him a 0-1 string. But we got to tell him all this information. So how do we tell him that information? We just give it to him as a 0-1 string, right? Here, we need to give him some input. What's that input? Well, we just give him a description of M and a description of I, right? Now, what do we want this oracle to do? This oracle will tell us whether M star halts on this input. We want M star, when do we want M star to halt on this input? We want M star to halt on this input when this M halts on this input, or when M halts on I, right? What do you think M star is? Tell me a Turing machine, M star, that if you give it a description, it's the universal Turing machine, right? M star is the universal Turing machine. Why? Because now it's going to just tell me whether M stops on I, right? If I know what's the universal Turing machine going to do? It's simply going to run M on I. And the universal Turing machine will halt if and only if M halts on I. Right? That's it. So that was an easy one, more or less. Easy one, yeah? We can pass it any string, right? Yeah, well how was I given M and I? I was actually given it to me as a binary string, right? So I was given a binary string, which my precondition is that it's interpreted as a Turing machine in an input, right? Now I get to give this guy a binary string where there's no precondition on it whatsoever. Yeah. Everything's a string of zeros and ones, right? If you're in computer land, then there are no elephants in this computer. If you want an elephant in the computer, you have a description of it, and that's basically a string of zeros and ones, right? I think we're going to do, okay, here, I actually, when I said I didn't change the slides, you might not have this in there because I grabbed these from below the line, right? There's the purple line. And one of the things that I decided not to harass you about is this whole before it, and not just does it decidable or not, but does it accept things, recognize things, co-accept, and all that. We decided to move that below the purple line. So, but then this is a pretty important one, just so that we make sure we understand what's going on. All right. So look at these two problems. Tell me this problem. If M halts on I, I'm supposed to say yes. And here, if M halts on I, I'm supposed to say no. These problems are complements of each other, right? So remember, we proved that the set of all regular languages is closed under complement, right? If L is regular, then L prime is regular. We look at the set of context-free grammars. Is it closed under regular? No. L can be regular, and L complement could be not regular, right? We look at the set of the side of compute. Is it closed under complement? If you can write a Turing machine that will say yes in these cases and no in these cases, can you rewrite that to a Turing machine that says just flips the yeses and the nos? Yeah, you can. No problem, dudes. All right, so now there's this class that I'm not going to talk about over here. Regular, what are they even called? Accepts versus recognizes, right? It's either accepts or it's recognizes. And these ones, the whole thing problem lives up here. Why? Because if M halts on I can run it, and if it's a yes instance, I know it's a yes instance, right? But if it's a no instance, I don't know it's a no instance. While over here, we have not halt, right? I promised I wasn't going to teach it, and here I'm teaching it. But the point is, if you go below the purple line, then you're not closed under complement, and so you can't do reductions like this. And we're not going down the purple line. We're living in here. So you can do reductions like this. All right? So let's talk about how to do a reduction like this. I have an oracle. What does this oracle do? Yeah?
Why are we looking at it if we're not going to do it?
I'm just doing a reduction here, and I'm showing you that decidable, the computable problems are closed under complement. We're not going to do this and this. We are going to do that the computable problems are closed under complement. Right? So I'm given an oracle that solves this problem. I want to come up with an oracle that solves this problem. Right? What is this problem? It's given an M and an I. You want to know, does M halt an I? What are we going to give this oracle? We're going to do an instance map. We just give it the same M and I, right? We just give it to it. Right? And what does the oracle do? It says, yes, it doesn't halt. Or it says, no, it does halt. Right? And what do? We just flip the answers. Right? We flip yes and no answers. And that's it. We flip yes and no's. To prove it's undecidable, it's okay to flip yes and no answers. Right? And the reason I'm telling you this is at one point I talked about reductions, and I said you have to map yes instances to yes and no to no. And you have to do that if you care about here versus here. Right? And if all you care about is do I live down here, then it's okay to map yeses to no's and no's to yeses. And that's my point. My point is don't worry about flipping the yeses and the no's. In fact, let me say that again. Don't worry about flipping the yeses and the no's. Well, when the oracle says yes, you say no, and when the oracle says no, you say yes. It's kind of like when you're 3 and you're talking to your mother. You know? I think you can do it. I think, in fact, I give you the, here, we do an instance map. We ask the oracle. Here, if the oracle says yes, we say yes. If the oracle says no, we say no. You just flip it. You can do that. We run out of time? Yeah. All right. Any questions about the test?
Yeah.
Yes?
So to clarify,
We're doing context-free grammars. You got to know, can a context-free grammar do it or not? If a context-free grammar can do it, you got to give me a grammar. If it can't, you got to argue that it can't. Why? Because the links overlap. Right? We got to do the halting problem. You got to be able to prove the halting problem. You got to be able to do reductions from the halting problem. What else have we got? Oh, counting. Infinite sets, countable infinite sets, uncountable infinite sets. What other topic? We're listing topics right now. We got another topic? I think that was it. Was that it?